Okay, we are super excited to have Kevin Leighton Brown here to give us a talk, and also he's here for a couple of months. Kevin is one of the top people in the world at the border of computation and econ. He's very well known in a variety of areas. He has come up with some of the most widely used auction mechanisms. He is doing great stuff in Africa. He's doing really, really amazing things. And I'm sure that all of you have already enjoyed and will continue to enjoy getting to know him. His talk is Economics and Computer Science of a Radio Spectrum Reallocation. Oh, so you're going to be talking about this. Fantastic. Yes, this was the big deal auction that I just mentioned. So, right? Yes.
Yes.
Yes, fantastic. So we'll hear about it right now.
Thanks. So what Jennifer was just suggesting there is that I came here in June and gave a talk in this same room to probably many of you, and I wanted to talk about two things. A market that I've been working with a bunch of people, including actually Nicole Imralika, who's here, on agricultural trade in Uganda, and an auction that I was involved in with mostly a team of economists at Stanford and the Federal Communication Commission to repurpose radio spectrum in the United States and Canada. And you guys asked so many interesting questions that I just completely crashed and burned the second half of the talk and did only the first half of the talk. And so I'm excited to be back here today to give the talk that I thought I was going to give last time. And I hope you again give so many interesting questions that I only do half the talk. That would be great. We can just keep this going forever. It'll be like a no, it'll be like a loaf of sourdough bread. Every time we'll keep part of it and use it for the next one. So please do feel free just to interrupt me as we go. This talk is going to be based on two recent papers that describe a kind of long thread of work. One of them is Proceedings of the National Academy of Sciences paper with Paul Milgram and Ilya Segal on the kind of economics of this problem. So those of you who might have seen earlier iterations of this talk, I'll be speaking more about the kind of economic design side of things here than probably what you would have seen in the past. The second half is on a 2018 Communications of the ACM paper with Neil Newman and Alex Fréchette about the kind of heuristic algorithm design that kind of fueled our part of the contribution to this auction. Neil Newman is a PhD student of mine who's also in New York right now visiting NYU, coming by the lab from time to time. So if you see him, he's the guy. So I don't think I turned this on. That's too bad. Okay, so I guess I mentioned some of these names, but the first half of the talk, particularly leverages work with Paul and Ilya. The second half, particularly Neil and Alex, who are students. Alex got poached by Google, and as I hear happens from time to time, but made big contributions to the first half. And I would be remiss if I didn't, at least kind of gesture at the huge number of other people who were involved in making all of this stuff go down, including an amazing team of people at the FCC who really deserve praise and adulation for having been willing to listen to a bunch of academics about something at which tens of billions of dollars was at stake. I think they've really been leaders in the U.S. government in being willing to think about crazy algorithmic solutions to important problems, and lots of other collaborators who touch things here and there. So what I want to talk about is an auction that the Federal Communication Commission held over 13 months between 2016 and 2017. I'm very sad to say that it was called the incentive auction, which if you have anything to do with auctions, you think that's a sad thing. But in fact, this name was given to the auction in legislation from Congress, so there's really nothing we can do about it. Although the name of the auction is, would seem to show no understanding whatsoever of auction theory, the auction itself is a pretty amazing idea. So basically, the idea is that over time, the Federal Communication Commission has been taking blocks of radio spectrum that nobody was using for anything and selling them off so that your phone can work faster. And that's been a great thing, but they've essentially run out of colors of light to sell. There's just only so many different wavelengths of spectrum out there. And so we got to the point where they needed to do something else if they wanted to give away radio spectrum. And what they decided that they could do was to look at some of the spectrum that was allocated at the very earliest days, which was, after all, spectrum with pretty good propagation characteristics. It travels long distances and penetrates concrete pretty well. And this was given away to television stations back when that was the main usage of spectrum besides radio. And it turns out, how many people in this room get their television signal over the air?
People in this room have a television.
Well, I saw a hand, so good for you. You're a leader. Actually, you're. Yeah. So I mean, in fact, there's like digital TV in the United States now. Like it's not a crazy thing to do, but not very many people do, and so it seemed like maybe it was a good idea to not have quite as much of the spectrum devoted to TV broadcast as it used to be.
If you have a dish on your roof, does that count over the
No. No.
It is air.
Okay.
Definitely.
But it's a term. Over the air is a term of art, and it doesn't mean the dish. It means UHF channels.
It also includes wireless internet for Netflix.
Correct. Another good point. All of these things are fine. We can keep that. The thing about wireless internet is it doesn't travel very far. It's an unregulated spectrum. But there's this, these protected blocks of UHF channels, which means nothing else can use this spectrum anywhere. And so what the government decided to do was to buy out some, but not all, of the broadcasters, so that they could still, the diehards who are still getting broadcast TV could still get it, but some of this spectrum could be sold off to more useful uses. How many people sometimes watch things that were broadcast on a TV on their cell phones? Any of you? Yeah. So maybe we should have more spectrum being used for that. So that was kind of the idea. And in the end, this auction did happen. It yielded about $20 billion. About half of that money was paid to television stations that voluntarily decided to stop being broadcasters. They're still allowed to use cable or use the internet or use whatever they want, but they stopped broadcasting signals over the air, and they sold their licenses. The stations that didn't decide to stop being broadcasters were potentially assigned new channels. So the reason Congress had to pass a law is that these non-participants are being assigned different channels, and the government pocketed the difference to pay down the national debt. That's a complicated question. Alex's hand was up first, so let's see what it.
About that too, but actually I would ask that wasn't this transition related to transition from like analog TV signal to digital TV signal?
No, that was something different, although that facilitated this. Something that's good about the transition from analog to digital is that you can actually change what frequency a channel is on without changing the apparent channel number from the perspective of the customer. So it can still say that it's channel 4, wherever it is in the band, and that's useful if you have a little logo that has a 4 on it.
But doesn't it take like less bandwidth?
It does, but they still had a right to the bandwidth that they had. So some of the channels are going to end up negotiating channel sharing agreements with each other, where they pack 2 channels into one band, and then they just have degraded quality. The alternative is they can have higher resolution, and it's up to them which they want. So it might be that some of these channels that sold their stations are going to end up channel sharing with somebody else. We don't know at this point. Yeah.
How much did the broadcasters pay originally to get these channels that they got given $1 million to give back?
So in this, as with many of the things I'm going to say today, it's a good time to stress that I'm not a representative of the FCC, and things I say about how the government in the United States operates are quite possibly wrong. But as I understand it, they paid nothing at all. It was a pretty good deal. Well, So I think initially the government was interested in there being television stations, and it was a costly thing to build the infrastructure and to continuously operate it, and it was seen as a public good. And so I think basically in the early days they said we would be willing to provide this public good. Here's our application, and the best applications were granted the licenses. And I'm getting ahead of myself, but it was in fact a little bit. In fact, maybe it's on the it's on the next slide. So let me come back to that point just in a second. But so So Congress decided to do this thing, and they decided a little bit about how it would work, but they didn't decide very much. So the team that was working through this consulting company led by Paul Milgram called Auctionomics had really unusual latitude in deciding how to design this auction. So when we think about mechanism design, often we see the problem as being quite formalized in terms of I have these things to allocate to these people with these utility functions. But here there's a lot more at play because it wasn't quite clear what participants' property rights in these things they were originally in the 60s given licenses to even were. It wasn't clear what the goods to be traded in the market should have been. It wasn't clear how many goods should be traded, how many stations should be bought out and how many should be left on the air. And it wasn't clear quite what the government should be trying to achieve here. So they told us they cared about efficiency first and foremost. They wanted to put the spectrum to a more socially valuable use. But they clearly also cared about revenue. They wanted to show the public that they were paying down the national debt through this reallocation. They wanted they cared about who ended up buying telecom licenses in the secondary market because they wanted to prevent oligopolies in the cell phone market. So they wanted the increase in spectrum to help some of the more marginal carriers to become more viable. And they also cared that the mechanism itself encourage participation by television stations, some of which were owned by sophisticated conglomerates, but others of which were small mom and pop operations that were going to be scared off by market complexity. So somehow all of these things needed to be balanced together to decide what ought to be done. And I think in that sense, certainly for me, and I hope through me to you, this was a really useful kind of case study for understanding what kind of market design looks like when you have more flexibility than you often would. And I guess the reason that I got to have a seat at the table with a bunch of economists who know vastly more about market design than I do is that it became clear very early that computational tractability was a really fundamental concern in this market. So it just wasn't possible to first of all design a market and then start thinking about computation because as I'll show you, that just bit pretty hard. So now coming to the point that I promised was on the next slide, it wasn't entirely clear in law what property rights the broadcasters actually had to their broadcast licenses. They were granted these licenses, but it wasn't clear whether they had them forever, whether the government had the right to take them back if it wanted to do something different with the spectrum. There was some discussion about this before I got on board, but it was clear that if the government had just decided to confiscate and repurpose, everything would have been tied up in the courts for a long time, and many people would have been unhappy. It might have been politically impossible to do. So there was a decision made not to do that. Conversely, there's a famous argument from Coase, who, after all, was in fact writing about the Federal Communication Commission when he made this argument, that if you want to end up with an efficient allocation of a resource, you don't need a central authority to get involved and to be making an allocation decision at all. All you need is to establish clear property rights and then basically let people trade with each other. And the market will sort everything out and good things will happen. And depending on how much of a true believer you are, you might believe this to a greater or lesser extent. Certainly, when I gave this talk at the University of Chicago, this is the place where they talked to me for 20 minutes about why did we do anything other than let the market just sort everything out. If Glenn were here today, he would represent that point of view avidly to all of you, as indeed he has to me in the past. But the catch in Coase's argument is that this only works when there are no frictions. And unfortunately, there's a critical friction in this market, which is holdout power. So the problem is any individual station could hold out and demand more than its marginal value because we have this kind of combinatorial value across the whole allocation. So the key problem is that if I bought out a set of television stations, I would have this sort of Swiss cheese of spectrum where there would be lots of little holes all over the place. And the way the technology works for wireless is I need a big contiguous block of spectrum to be useful to a wireless company. So this is sort of like real estate, where people have thought a lot about holdout. If you want to build a big skyscraper in New York City, you need to buy out the whole block. It's not good to have lots of little businesses here and there. And if you've bought out almost the whole block, then that last business you haven't bought out yet can demand a really high price because it knows that it's what's standing between you and your skyscraper. And so kind of the same thing could happen here. And that can be a big problem for efficient allocation. So the way this problem got addressed in the FCC problem was through a really clever redefinition of property rights. So what ended up being decided was that stations didn't in fact have a property right to the particular frequency block that they were broadcasting on. What they had a right to was to be broadcasting on some frequency block with interference characteristics that were similar to what they had before. So if you right now have a license to channel 14, you don't have a God-given right to channel 14. You have a God-given right to broadcasting from the tower that you currently are broadcasting at, on the signal strength you're currently broadcasting at, reaching the people you're currently reaching, but maybe on a different channel. And that's the property right that was instituted in this particular bill from 2012, which this is a graphical depiction of it. And this was, I think this might no longer be true, but I think at one time this was the least productive Congress in history because it passed only 7 bills in all of 2012, and this was one of them. And everything just got stuck into this one gigantic bill. And so, among other things, they created this spectrum auction. And so they said, and this is a big deal for the holdout problem because it says we don't have to buy out a specific set of stations, we just need to buy out enough stations. It's sort of like if I could move around the businesses in New York City, shuffle people around and say, well, you used to have your store here, but I'm going to move you a block over so that I can build my skyscraper. And you see that would make the problem of getting up enough land to build your skyscraper a lot easier to do. And so in economics jargon, this makes stations into substitutes for each other, where they weren't before. And that makes competition more effective. So another design question we had to care about was how much spectrum we should clear. So in this project, everything was more complicated in the details than it seemed like it would be in the first place. And this is true in the question of band plans, because it turns out one question of how much spectrum to clear is, which amounts of spectrum to clear are even feasible given all the crazy constraints. Turns out, for example, that channel 37 is reserved for use by radio astronomy. This is a true story. So the radio telescopes need to have a chunk of spectrum that is not used for anything else all across the country to avoid interference. And there also needs to be a 3 megahertz guard band on either side of channel 37, again, to protect everybody from each other. So that kind of complicates things. And then it turns out that the wireless people really need uplink bands and downlink bands that are separated from each other, and everything needs guard bands, keeping some room clear. And then it turns out that the shows on Broadway really care about using unregulated spectrum for their wireless microphones. If you ever wondered how is it that you can hear what's going on in a Broadway play, it's unregulated UHF spectrum that is being used for wireless microphones. So there was a huge lobby pushing for enough unregulated spectrum that was particularly driven by them, and all of this crazy stuff. And the sausage got made in an incredibly complicated way. And I was sort of a silent participant in some of these conference calls, and it was just unbelievable how much was going on. But they came up with something very sensible, which was this particular set of band plans that said, so these are television stations. So channel 21, 22, 23, up to 29. It's right now we have up to 52 in the original UHF band. So this said, let's get rid of everything north of channel 29, and then all this blue stuff is what we're going to create, which is new license blocks that we can sell. So this is licenses A through J, uplink bands and downlink bands paired. So if you buy A, you get both of them. And then they're over kind of big geographical regions, but notice that these are nice and clean and contiguous. And so, which of these should I have? Like, should I end up clearing 126 megahertz of spectrum, or should I end up clearing 72 megahertz of spectrum? It's really hard to say. You try to figure it out by talking to people and saying, how much do you need? How much would you be prepared to pay? but there was so much political posturing going on where, some of the broadcasters were saying we would never sell, and others were saying, please, we really want to sell, and some of the telecoms are saying we really want to participate, and others said they wouldn't, and it was really hard to know what was going to be feasible to do. So what ended up, yeah.
Just in terms of your depiction, like the 11s and the 7s with the hash, those are guard bands?
That's an 11 megahertz wide. It's sort of both a guard band and it's a trunk of unregulated spectrum. So that's also how Wi-Fi works. So Wi-Fi is in a set-aside chunk of unregulated spectrum. But yeah, so it also serves as a guard band. Yeah.
I mean, why would you move where the 11 is, depending on how much you're selling?
Well, you want it to be in between the uplink and downlink.
I see. Okay.
And what about the 11 between the A and 39?
I guess you need another guard band between the TV stations and the beginning of the telecom, and just I guess how much of it you have sort of depends on having things be the right width. So I think we wanted these to all be 5 megahertz wide, and these were all 6 megahertz wide, and 37 happens where it happens, and so things just sort of lined up differently in the different plans. Yeah. Sorry, can you say that again?
Why is the clearing pointing up?
Why is it pointing up? Because we start, because I guess in what I'm just about to say, we started out over here. This was the first thing we tried, was to clear a lot of spectrum, and if it didn't work, we progressed to clear less and less. So what you would kind of want is to say, how much stuff should I trade? I want supply to meet demand. And that's tricky here because we don't have a homogeneous good. So there isn't a single price at which I can talk about whether supply and demand line up, because all of the things being traded cover different populations. The wireless licenses are all different from each other, and the things being bought and the things being sold don't even correspond to each other. There's this kind of alchemy that goes on where somebody sells me one kind of thing and I turn it into another kind of thing before I sell it. So this notion of supply and demand meeting is a complicated thing. But eventually what we did was, I'll tell you about it more in a little bit of detail later, but effectively what we did was to try to clear a lot of spectrum, sort of see what happened if it met some conditions that meant that we were happy with the outcome. We would just do that because we were trying to clear a lot of spectrum. If it didn't work, we tried to clear a little bit of less spectrum and sort of work our way up. And
in terms of geography, that the inhabitants of all those slots might, at different locations, you might choose different rows in this design? Or?
No, so we did one thing nationally.
So one thing nationally, and then in some sense, but the who lives in each slot might differ nationwide, or also is the same for
these were different in different parts of the country, but they were relatively big parts of the country.
Okay.
So I should say in the actual auction, what happened was that this went for 4 steps. So we ended up clearing 84 megahertz of spectrum. So this particular story here is the one that actually happened. There's a more complicated story to say about why that might have made sense, but let me skip it. So another really important question from the economics perspective is the question of externalities. So you want to try to define your property rights in a way that says, when I'm thinking about different allocations, all I care about, the sort of sufficient statistic for an allocation, is what I get. And I don't, given a statement about what I get, I don't care about what everybody else gets at the same time. And in this context, what the way that property was brought about was to say, if I get given a certain station, then I won't. My assignment won't cause more than some minimal level of interference, which in law is defined as no more than 0.5% of the population for anybody else. So that's why nobody else should care about the rest of the allocation, because they're not going to get interfered too much. And that's essentially, that's sort of the bread and butter of what the FCC does, right? They sort of fundamentally care about regulating the use of spectrum so that people don't impose negative externalities on each other, so that one person's use of spectrum doesn't prevent somebody else's use. And this is the first place where computation starts to become a really obvious problem, because figuring out, when I'm sort of counterfactually thinking about different allocations, figuring out about whether I get into this kind of computational problem, interference problem, is a computational nightmare. So first of all, if I was just given one single allocation to think about, and I want to know how many customers are affected by interference from one station or another under some given assignment, this question takes days of computer time using an incredibly fancy simulation, particle simulation based on tiny, like 4-mile wide cells across the entire country, made by a bunch of radio engineers who work for the FCC. And they have to think about things like how much forest cover is there between this station and the population that it's serving, because it absorbs radio waves differently, and where are there hills, and how's the population. Notice this doesn't say half a percentage of the geographical area reached by the signal, it's the populations. You have to care about where people live. And so they actually have a way of doing this, but it takes forever. Yeah?
So does have percent constraint? So it has to, so say I'm a big broadcaster and I'm affecting only 0.5% of my population, but then there could be like a small broadcaster for whom we know my 0.5% is a lot more. So how is that resolved?
No, it's saying nobody that you affect has more than 0.5% of their population affected. Indeed, that it doesn't have to be symmetric because signal strengths can be very different.
Okay.
So, yeah.
So how dynamic is this problem? Like, is this a one-time thing, or how often do you
Well, I'm sort of building that up. I'm just saying, if you wanted to know, if you were just to, with pencil and paper, figure out an allocation of stations to channels across the entire country, and you were the Unabomber and you decided this was your secret plan for the universe, and you went to Washington to the FCC and you said, here's my plan, tell me whether this would work.
probably wouldn't get around to it?
Yeah, there's some problems with the logic here, but if all of that happened, then it would take them days of computer time to give you an answer.
This is a large instance of a sharp P problem.
Yeah, it's possibly even. I think we're going to sort of reduce it to that maybe at some point. I mean, the way this simulation actually works is possibly even worse than that. But with some work, we're going to get down to simply intractable problems.
Okay.
I mean, this is essentially like a numerical. It's sort of like the way weather simulation works or something. I don't really know what the complexity of that is. But then, of course, as bad as that is, now we can start thinking about kind of combinatorial arguments and saying, of course, there are many different ways that I could come up with possible allocations. There are combinatorially many. The size of the problem we had to care about was every television station in both the United States and Canada, because, other fun story, they managed, as this whole process was going on, to negotiate with the Canadian government and decide that Canada would get repacked too, because inconveniently, the Canadian population lives almost entirely along the border with the United States. And so if they didn't move the television stations in Canada, they would interfere across the border, and the border was a terrible problem for us. And so basically, Canada actually didn't do the auction at the same time, but they said, we'll do the repacking at the same time, so we'll end up with this beautiful contiguous spectrum that you guys are paying to do anyway. We'll just have it for free, and then we'll sell it off later. So, but that meant we had more stations. So we had almost 3,000 stations we had to repack. And, it depends on the band plan, how many things I have to repack them into. But let's take the smallest example where I have to repack them into 126 target, where I have 29 channels. Even in that smallest example, I've got, 10 to the 4,300 different combinations that I might have to care about, which is a very big number. So it probably wasn't going to work to brute force search this. The first thing that I'm very happy that I managed to persuade the FCC to do was, rather than caring about aggregate interference across all, so something that I thought Alex was going to object to, that you might worry about is, well, Alex only affects my 0.5% of my population, and Jennifer only affects 0.5% of my population, but they might not be the same 0.5%, right? Many people might interfere with me, and they each might interfere with me up to 0.5%, which means that I might have kind of a lot of my population eaten away at by all of this interference. And so if you're really a stickler for this minimal interference criterion, you might say you have to care about everybody in the aggregate who interferes with you. And if you do that, you're sort of forced to be running these simulations all the time, and the world is a terrible place. And so we managed to persuade the FCC not to do that most precise thing, but instead to say you only have to care about pairwise interference, and you don't have to worry about how these things compound. And we looked at simulations, and we found that it doesn't happen very often that these things stack up in a bad way. And if they do, you can try to mitigate it after the fact. But we only thought about these pairwise constraints, and that let us think about a kind of graph coloring version of this problem, where we say, I now want to ask, I have these pairwise interference constraints that say I'm not allowed to be on channel 14 if Alex is on channel 14. And in fact, it's a little bit worse than that. It's a sort of slightly complexified version of graph coloring, because I'm also not allowed to be on channel 14 if Alex is on channel 15. So we have these sort of side constraints as well sometimes. But then I can say, is there some way of coloring this graph with channels so that none of these interference constraints get violated? And now I've got an NP-complete decision problem to ask. So I finally fought my way down to an NP-complete problem. Life is good. This took a bit of explaining to the FCC, but again, this is not something that we can guarantee is always going to be awesome. So, so this is sort of a second response to the sort of University of Chicago types to say, if I believe that in its wisdom the market can somehow figure this out, then I somehow believe that in its wisdom the market is running an efficient distributed algorithm that solves NP-complete problems all the time. And so there's sort of a complexity theoretic argument against Coase's theorem, even if I wasn't worried about the market frictions from holdout. And so essentially this is why we need a central authority like the FCC and careful market design. Yeah.
I'm interested in this. So I mean, why is it essential here that an algorithm is distributed? I mean, like even the centralized problem is facing equals to.
No, I'm saying like people just doing random things in the market, and by the invisible hand getting to an efficient allocation would be interpretable as a decentralized algorithm.
Oh,
obviously we weren't running a decentralized algorithm. We were just running some centralized thing.
I understand, but in the end you were running a heuristic that was doing things pretty well, and why isn't it completely impossible that there exists a distributed heuristic that accomplishes the same thing?
I guess I can't argue against the hypothesis. Why is it completely impossible that there exists?
I mean, why is it really, really less likely to?
I think you're misunderstanding the language on the slide. The place where I'm using the word decentralized is talking about why I don't think the market can do this. I'm not saying we couldn't make a decentralized algorithm. I'm just saying everything we know about solving NP-complete problems is that decentralized algorithms are not some kind of magic that is super better than a centralized algorithm.
Sure.
That's all I'm trying to say here. So here then is how the auction actually worked. So there was a so-called forward auction for telecoms to buy spectrum. And this basically worked the way spectrum auctions in the past have worked. So there was a little bit of innovation in this part of the design, but it was essentially following this kind of tried and true clock auction designs. Then there was a reverse auction for broadcasters, which was like a procurement auction where we were buying spectrum. And this was completely new. This was something that really hadn't ever been done before. And that's what I'm going to be on this slide, be talking about. And so this had descending prices. Where people kept accepting offers. I'll tell you a little bit more on the next slide.
The price for giving up your right
That's right.
Or for being moved, or being moved. As
No, you have no choice about being moved.
I see. So if you don't sell, then you're.
What? So everything's always more complicated. So.
Domain, right?
Well, it isn't really eminent domain because it's sort of a definition of your property right that says we're giving you something that is sort of nominally different, but it's the same. You ought to think it's the same. And some of you were wondering what happened to the $2 billion that all the numbers that I gave didn't add up. Actually, part of it went to pay for the high-priced consultants who work for the FCC, but most of it went vastly to a first-order approximation. All of it went to station retuning costs. So basically, those stations that got moved, it costs money to get moved. And so the legislation says the FCC is going to pay those costs. So that's part of why you shouldn't care about being moved. And so basically you do these two things kind of in a decoupled way, and you say, let's say I'm going with the 126 megahertz band plan. Let me sell off that spectrum, and then let me buy that spectrum. And then let me look at what I just did. And did I just spend more than I earned? And if I did, then that was a terrible mistake. And so let's not do that. And if, on the other hand, if I made at least $2 billion, which is what the legislation said had to happen, then cool. Then that's what happened. Then it's going to be real. And so that was iterated, as it turns out, 4 times until eventually that condition was met at 84 megahertz. So now let me, pardon me.
Can I do some arbitrage on that?
You tell me. Basically, each phase picked up from the previous stage. So all of the bids that you make in one round are just resumed into the next round. So if you're a forward auction participant, you're just bidding for less stuff than you were bidding for before. And so prices are just going to go up because there's all of a sudden more competition than there was at the moment when the auction ended. If you're a reverse auction participant, you're in a procurement auction and the government has just decided to buy less stuff. And so prices are just going to keep falling. So I don't think there's an obvious way that you can manipulate that. Yeah.
So you ran it once and didn't make $2 billion, and you ran it the second time and didn't make $2 billion, and the third time it didn't make, and the fourth time you made $10 billion?
Yes. Well, in the first time, in fact, I think in the first 3 times it lost enormous amounts of money. I think the first time I think it lost $65 billion.
What?
Which is to say, it cost, the difference in what it cost and what they were able to get in revenue was an enormous amount.
But they didn't actually.
No, I mean it like nominally lost. Like had that been what happened, yeah. Yeah. No, I mean they didn't actually lose any money, but it isn't like it was like 0, 0.1, 0.52. Like it was wildly negative, and then eventually came into positive territory.
So was it just, as you keep doing this, broadcasters learn that they can't ask as much as they were asking, and
it isn't. I mean, it doesn't have to be a story about learning. It can.
I thought they were allowed to change their offers.
Yeah. So I think it's partly that if I want to clear a lot of spectrum, I might have to buy out some really expensive broadcasters. And as I need to clear less and less spectrum, I need to buy out fewer and fewer people, coupled with a story about how much demand is there for this spectrum. How much does the marginal wireless company want this spectrum, and how do those guys compare with each other?
So wait now, you didn't do this continuously because otherwise you would have ended up at exactly $2 billion revenue.
That's right. That's where these band plans kick in, that there really were only discrete points that made sense.
And it was agreed that you stopped the first time. You could sort of say, I want to make more money, so I run it another.
That's right. Now, if you're following along really carefully, you'll notice that it's not actually guaranteed that the amount of money you make will go up. It is guaranteed that per license you'll make more, but you're also selling fewer licenses every time. And so depending on the shape of the demand curve, if I sold just 1 license, it's not clear that would make yet more money in the aggregate than when I sold 6 licenses nationally. So it could be that if you did what Christian proposed, you would actually lose money, or it could be that you'd make money. But regardless, there was an efficiency objective.
So that could have happened here in general.
Yeah, and then that would have been a real disaster. But there's a bunch of
it wouldn't happen.
A lot of economic modeling. I mean, people thought about like these things. They're not selling like something that nobody's ever written a paper about before. People know something about the wireless industry and the TV industry, and they studied it enough to be pretty confident that this was going to be okay. But there wasn't a theorem that said that the prices were going to monotonically go up. There's actually probably some condition in the legislation that said what would have happened if the prices didn't go up. They probably would have just called off the whole auction and said, we didn't find a feasible point. Yeah.
Is it normal and okay to, like, it sounded like in between the 4 iterations you were kind of changing the rules of the auction by, reducing the band?
Well, I mean, all of this was in the rules. I mean, this was all in the rules of the auction. This whole thing was the auction.
This will happen. And
Yeah.
Okay.
Yeah. I mean, maybe I'm sort of personifying, we didn't do it after all. But no, I mean, there's like some, 362-page document that says how the auction works, and this was all in there, and much more besides. But let me tell you how the reverse auction works, because it's interesting. So I mean, personally, I found like for the first 4 months I was involved in the project, I just kept getting turned around with the reverse auction because somehow putting minus signs in front of things is very complicated. Like, so, auctions in which you buy things are complicated. The constraints work a little bit differently. So I concocted this example to try to make this make sense, and I hope it helps you. So let's think about the problem of airline overbooking, because this is something that's near and dear to most of our hearts. So and let's add one unrealistic constraint, which is that passengers have to either fly in the cabin that they were assigned, or they have to be compensated and give up their seat. So there's no notion of being bumped from economy into business class. You just either have to fly in your assigned cabin, or you have to get bought out by the airline, just because that'll map better onto our problem. And so we then have a feasibility constraint, which is that the number of people in a cabin has to be less than or equal to the number of seats in the cabin. The plane can't take off if that's not true. And we're going to use the same auction mechanism. And so the way it works is, we start out with a plane that's big enough to hold everybody. So here's a kind of schematic picture of my plane. This is like, radio, TV stations in the United States circa, 1995, whatever, 2016. And there's enough room to hold everybody. And then, of course, the airline says, we're losing fuel, flying this thing across the Atlantic. Let's substitute in a smaller plane that no longer will hold everybody. You've probably been in that position. I know I have. And so what do? So then, American Airlines here says, well, we just substitute in a smaller plane. There's no room for all of you. But hey, what if we offer you $1,000 and you fly in the first flight out tomorrow? And some of the people say, that sounds pretty good to me. I wouldn't mind having $1,000. I wasn't in a hurry anyway. I'll see a Broadway play with some of those fancy wireless microphones. Some other people say, no, I really, need to give a talk at Microsoft. In this auction, you do, but watch what happens. So all these people go out, but then the airline says, I kind of overachieved. I bought out a lot more people than I needed. We didn't get to be American Airlines by paying people more money than we had to. So I was just kidding about the $1,000. Let's make that $800. How do you guys feel now? That's why it's an auction, right? And so then some of the people say, well, you had me at $1,000, but not 800. And in particular, the first class people maybe are not that motivated by money, so they just go back on the plane. And now I've got a problem, because these first class people, I've got nowhere to put them. But on the other hand, I didn't fill up business class or economy class because these people still liked the $800. And so what that means is I'm stuck paying these guys $800 because I have no alternative. And so they've accepted an offer for $800. I filled up the plane, so I have to make that offer. I have to realize that offer. But these other guys, I don't have to. So for them, I say I was also lying about $800. What about $600? Some more people go on the plane, but it doesn't quite fill up. I keep lowering it until I fill up business class and I lock in another price. But then these losers in economy class that they'll just do anything for sort of peanuts and a free water. So I keep lowering the prices and packing them in like cattle until eventually I lock things down at a lower price. And notice that the way that I arrive at these different prices has nothing to do with the relative value of an economy class seat and a first class seat. It has to do with the price sensitivities of the other people in that class. And so that's the sense in which this is an auction that's discovering these prices. And there are a lot of broken hearts from all these people who saw the prices fall. But at the end of the day, you're being paid something that has to do with what it would have cost to buy out other people in the right amounts. I saw a hand. Do you still have a question? Or?
I know you answered.
Cool. So this is pretty much like what happens in the FCC auction, where these different.
No, it's not. You can't do that, right?
No.
There's a rule.
Oh,
which
God
says,
knows they beat you.
No. But there's this.
Yeah, they have to drag you off and break your teeth instead, right?
There's this triple compensation rule that you have to pay me 3 times the price.
That's why it's an example. But
You should offer this to the airline.
yeah, I'll be the most popular person in the world. But
Under Trump, it's not hard to change the law.
that's true. We'll leave that for the discussion afterwards. But I want to say these different classes of service are not like better pieces of spectrum and worse pieces of spectrum. They're basically television stations that share constraints with each other. And so what causes them to share constraints is that they're geographically in the same place. And so there might be some places where the other stations have relatively high values, like New York. There might be other places where your competing stations have relatively low values, like the Midwest. But it isn't necessarily, what's your population or how great is your station. It's just more, how much are your competitors willing to pay. The way that it's different is, in order to make this example coherent to you, I had a very simple uniform matroid constraint that just said, I'm going to count the number of people compared to the number of seats. This is the actual constraint graph. So every station is a little bit different from every other station because, if you're 2 blocks over that way, then, you might interfere with a different set of other people. And so you've got edges in the graph that other people don't have, or your signal strength is a little bit different. And so things are incredibly messy and complicated. It turns out in New York, we had stations with a degree in the graph of something like 150. So they interfered with like 150 other stations, ranging all the way from kind of Connecticut to, Pennsylvania. So yes.
You have to buy them out where they are now, but other ones that come in will be at different locations.
Well, we only had to worry about the ones that we have now. I mean, the market can sort of do what it wants, trading things around and approving new licenses after the auction happens. This is kind of a snapshot in time right now.
Okay, and what about if stations own multiple locations with the same bandwidth, then they're not interfering with each other? Like if someone had a Philly in New York that was the same, is that taken into account, or is that not normally?
So what are you saying, that one company owns multiple stations
with the same spectrum number? Because then they're not interfering with.
Well, they have the same channel number. After the auction, they might not end up on the same underlying spectrum, but the customers will have no way of figuring that out.
They will interfere anyway with each other. I mean, you're saying that there is because they're in the same company, they have an additional strategy to avoid interference?
Yeah, right.
Yeah, there isn't really a way of doing that. Like every television, like right now, this graph on the 52 channels, nobody's interfering more than 0.5% with anybody else. Like the FCC has arrived at a feasible allocation on the 52 coloring version of this problem. And the question is, let's find a 29 coloring of this problem on the same graph. That's not possible to do. And so what you have to do is, like in the airline example, you offer a very high initial price. You get a lot of people to get off the plane, and you come up with a feasible coloring. And then you say, I'm paying way too much. Let me gradually lower the prices, and gradually people are going to get back on the plane. They're going to re-enter the graph and get colored. And I'm going to keep lowering the prices as far as I can until things finish. Something that I wasn't clear about in the airplane example, but it's important, is that in fact I have to go round robin through the people. So I don't make the same offer to everybody all at once, because I might have too many people come back on the plane and there's no room for them. So I really have to do it one at a time. I just sort of simplified that. So what this means is every single time I want to go to you and make you a new price offer, before I do that, I have to make sure there's room on the plane for you. So what does that mean in the real auction? It means I have to say, given everybody else who's already exited the auction, who's already committed to remaining a broadcaster, and I know that I can color all of them. I can find channels for all of them. Can I find channels for all of them plus you? If the answer is yes, I can lower the price that I offer to you, because I know that if you say no, I can put you back on the air. If I don't know whether it's possible to do it, I have to be safe, right? Because I could screw up. You could tell me no, and there could really be nowhere to put you, and I would have just broken, the entire television map in the United States. So I have to, in that case, just keep the last offer that you accepted. And so what that means is I have to keep solving these slightly different graph coloring problems over and over again. Every time I want to move one price for one person, I have to solve a new graph coloring problem, which is everybody who's been bought out so far plus you, is that colorable, yes or no? And in simulations, we have to solve on the order of 100,000 of these to run one auction. And of those 100,000, about 80,000 of them are trivial in the sense that I can take the previous assignment and then change nothing about it and just add you in. So we don't need anything fancy to solve those problems. Another like 20,000 of them, that doesn't work. You're going to have to start reassigning the channels you gave to other people to make room for you, which is fine. I mean, there's no reason we should be wedded to whatever assignment we had before, but it means computationally we have to do something a little bit more to figure that out.
Assuming that this is heavily, the outcomes heavily dependent on the order that you choose then to go through the stations?
It's not all that dependent because, as you'll see, these problems are almost always feasible. So they're going to be feasible kind of regardless. The problems I'm going to encounter will depend a bit on the order. Also, mostly people don't exit the auction. So mostly I offer you a lower price, and you say, I will accept the lower price. Because you only get to reject once. Right? If you reject the price, you go back on the air forever. So by and large, people in the auction are saying yes. And by and large, the questions being asked about them are feasible. So this is a giant graph coloring problem on a graph with 3,000 nodes, about 3 million pairwise constraints. And when I first got involved with the problem, the FCC didn't believe that it was possible to solve this problem nationally. They were investigating heuristic solutions that would say, let me only try to repack some little part of the graph. And that wasn't working very well because the graph is not very decomposable. Like the entire eastern seaboard is just incredibly connected. And so if you just cut part of the graph, you're cutting across a lot of edges, and that can hurt feasibility a lot. So we did it using an approach that I'll call deep optimization, and I think I'll make it just far enough to tell you what I mean by that. So before I get to that, let me say something cool about the market design, which is what happens if I can't solve an instance? This is an NP-complete problem that I'm attacking with heuristics. I'm not going to solve it 100% of the time. So, and in fact, if you do the math, we were told by the FCC that they needed a minimum of 2 price decrements per day, per business day, which meant that we got sort of 3-ish hours to run computations for each round to give people time to respond in the business day. And then that meant that we were given a budget of about a minute per feasibility check. So I'm trying to solve this 3,000 node graph coloring problem in about a minute. And I can do various things in parallel, but that can only help me so much on this enormous combinatorial problem. So what's really cool about this auction design is if I get a problem that I'm just not able to solve, I just treat it as infeasible. And let's think about what happens if I do that. That means I'm going to freeze somebody's price at a higher level than I should have. I'm going to freeze somebody a little early. And that's going to cause me to pay too much. But it's not going to cause some catastrophe for the auction. It's not going to cause an infeasible thing to happen in the auction. But if I can make my algorithm a little bit better, then I'm going to allow prices to fall a little bit more. And so this is the most compelling example I know of in heuristic algorithm design, where very slight improvements in quality translate really directly into money, because this thing is falling on a geometric clock. So if I can solve one more instance, that could potentially be worth like $1 million to the government. And so we were very motivated to make these marginal improvements.
Back to Dave's question. So if you have some beliefs about the bidder's reservation price, it sounds maybe more efficient if you start with the bidder who you are more certain with their pricing, then you can clear them out from the market very quickly. Then the remaining number of players will be smaller, then the computation will be less burden. I mean, in terms of ordering, you start with people they will take the price immediately.
That's true. It doesn't help as much as you would think it would. I thought a lot about this kind of thing. You can create crazy, so something I've glossed over here, but we care very much about the incentives of this mechanism. So there are certain things that if you do them, you can erode incentives. So if you change the order based on things people have done in the past, then you can, or even things others have done in the past, you can create crazy incentive problems. The reason it can matter what others have done in the past is that you can have sets of stations that are owned by one owner. So we were forced to commit to one ordering that was used repeatedly. You could try to optimize that ordering. In the end, we didn't. In the end, we would have actually liked to, but something was put in writing before we realized what we wanted to do that we were then not allowed to change because it had gone out to the public. And so we were basically forced to have one random order that we used repeatedly, the same ordering every time. But it actually wouldn't have made that much difference because exits are very rare. So in the chance that you could have actually made a change in ordering that would have bit is pretty small. A much bigger problem is whether you're going to figure out the problems are infeasible, because because what does tend to happen is that you time out on a problem. You don't know whether it's feasible. You're forced to freeze a price, and it could have gone a lot lower. So should I be stopping at noon or at 12:15? So I will stop at noon then. But let me say just very quickly what we did. So we took a bunch of simulations to come up with a bunch of representative problem instances based on actually running these things in simulation. On those problems, we first of all looked at MIP solvers, and we found out that they were terrible. That in our 1 minute cutoff, MIP solvers would have been able to solve sort of, depending on whether you chose Cplex or Gurobi, between like 15% or a third of all the problems across the whole auction, which really would have been awful. We then looked at satisfiability solvers, which I think is much more appropriate here because it's a purely combinatorial problem which is just a feasibility problem. We found that they got a lot better, but they still only got up to about 80% of problem solved. And this doesn't necessarily mean the 80% that get encountered first. So you actually ran this in a simulation, it might be worse. Then the thing that I will talk about in the talk that I give 6 months from now, yet again finishing the half of the talk that I didn't give, as I promised at the beginning, is the approach we made to design something for this problem instead. And I just want to kind of float this idea of so-called deep optimization. And to sketch this, the way that I understand the kind of deep learning revolution is that it said, look, what we used to do was to rely really heavily on design influenced by what people understand. We would engineer features based on expert insight. We would think about what's the best model family. We'd tune hyperparameters by hand. And we sort of moved to a world that said, let's just parameterize things like crazy. Let's use expert knowledge only to come up with things like inductive biases, but otherwise give ourselves a lot of flexibility. And then let's have lots of data plus appropriate regularization and lots of computation. And let's just search this thing like crazy and find some good point in the space we might not really understand. And I want to argue that we should design optimization algorithms in the same way, where heuristic optimization used to be approached much like classical machine learning, where it was based on kind of intuition and expert opinion. And I think instead we should come up with very highly parameterized design spaces for heuristic algorithms that are deep in the sense that we have many deep dependencies of how one parameter behaves given choices of others. We have a lot of data to characterize the kinds of problems we actually care about solving, and then we do really computationally intensive search to basically synthesize algorithms that are optimized to perform really well in our distribution. And fundamentally, that's what we did in order to be able to solve virtually all of these problems in practice. So we, based on our simulations, we believe we can solve about 99.5% of the problems that arose in these simulations. And I guess the last thing I'll show you, jumping through all the story about how the algorithm works, is what are the economic effects of what we did. Of course, we don't know, but we do have this great simulation engine that can say, what really would have happened given different valuation assumptions. And we can say, what if I only did the greedy feasibility checker, which just solves that 80% of trivial problems? What if I used Gurobi, which was our best mixed integer programming solver? What if I used PicoSat, which is a pretty decent SAT solver that people in the literature on this problem were thinking about early after we got involved? And what if we used the thing that we actually came up with? And these different points are 20 different auction simulations with different underlying valuations. And what you see on the x-axis is how much would it have cost the FCC to buy these different stations out? Oh, sorry, that's the y-axis. How much would this have cost? And the x-axis is how much worse was this than the very best thing you might have done. So how much efficiency loss was there? And what you can see is, and that's efficiency loss based on having done a single shot kind of VCG style optimization, which was intractable to do here. So that part of this efficiency loss comes from this iterative auction design that we had no control over. But you can see that this is pretty remarkable for an empirical result, that we're doing better in both dimensions, and there's a really crisp separation from these different approaches. So it looks like we're in terms of value loss, we were more efficient to the tune of like $2 billion. And in terms of what it cost the government, we're saving the money to the tune of like $5 billion just from the quality of the algorithm design. So on the whole, we think that this worked out pretty well.
So that ends up being more than the $7 billion.
Potentially, yeah. I mean,
The scale's the same.
yeah. So these simulations are, the best guesses people have in the literature about what station valuations really look like. For the exact stations that really do exist. Some people study these things. The accuracy, the magnitudes of these numbers depend on how much you believe those valuation distributions. But I think it's at least to the orders of magnitude, I think it's probably roughly right. Nicole?
I was going to make a similar comment that you said it cost the government $10 billion to buy out the stations in your first slide, and your simulations, it's costing them $2 billion.
Yeah, it was one. No, that was efficiency loss of $2 billion. Oh no, you're right. The cost was also $2 billion. That's true. So I think this is again based on 84 megahertz, but there's some things about the way that the auction gets set up that we don't simulate, mostly to do with initial conditions, which involve a crazy optimization the government ran that took 15 days to run to decide what the starting prices needed to be. And which prices, mostly in border regions, freeze. So it's true there's not an apples-to-apples comparison between what really happened and what we're doing here, but there is an apples-to-apples comparison between the green dots and the red dots. So presumably what that means is the green dots would also have been much worse than I'm showing here on the real auction. Yeah.
Can you just briefly say, for the eventual, you're saying that you're using deep neural net to synthesize an algorithm, right? What's this deep?
I went very quickly over it, but that's not what I'm saying. I'm saying I'm using an analogy to deep neural networks to motivate the approach that we're taking.
It's so every particular set of parameters for this deep neural net is an algorithm.
It's really not a neural net. There's just nothing neural about it.
Okay.
But what I'm saying is we're exposing an unstructured, highly parameterized space that we're searching using a powerful optimization approach using a lot of data. And I think that's a good idea for the same reason that I think deep learning is a good idea. The search procedure we use is not stochastic gradient descent. It's Bayesian optimization. Basically, we need to worry about two things that don't arise in the deep learning context. One is a lot of noise about the value of a parameter setting, because on some instances we might perform very well, and on other instances we might perform very badly. And which instances we run on is a decision variable under our control in the experiment. So that's one big kind of experimental design question we think a lot about. The other is the cost of actually figuring out how good a parameter setting is varies across parameter settings, right? A powerful algorithm is easy to measure the runtime of because it's fast. A really bad algorithm is very slow to measure the runtime of because it's slow. And so that's also something we need to think carefully about. That's what makes Bayesian optimization a more sensible approach, because it drives us towards good parts of the space. Broadly, this means we've thought a lot about kind of experimental design and kind of contextual bandit style problems in these sort of settings with asymmetric loss functions, which I know is something that people in this lab know a lot about. So that's something I look forward to talking to you guys about in the future. I think I'm conscious that I've gone 6 minutes over my allotted time, so maybe we should leave it there. But thanks for all of your great questions.